Hello, everybody, and welcome to this month's Future in Space Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute. And for those of you who aren't quite familiar with these hangouts, about every month or so, Alberto and Harley and I get together and discuss some of the things that we think would be of interest to be interesting to you guys for learning about the future. What's going on in the future, not just of space and science, but also space travel and human spaceflight and everything else. So we've teamed up with the American Astronomical Society and the American Astronautical Society to get their memberships involved to help us discuss some of these really important topics that many of the membership in these two organizations are working on. And so So today, what we're going to discuss is the future of space telescopes, and we're going to delve into topics like who decides what we're going to build, how do they get designed, and ultimately what are some of the challenges in getting them built. And so, joining me as he does every month is Dr. Alberto Conti. Hello, Alberto. Welcome.
Hey Tony, good to be here. I miss Harley though.
Yeah, Harley's on vacation this month and won't be back until next time. So, but anyway, how are you doing, Alberto? You are you're an astronomer, but you work with the Northrop Grumman Corporation, which is also very instrumental in getting the James Webb Space Telescope built, right?
It is actually. So we are the main contractor on the program, and we're very proud of working, for NASA in building this incredible observatory. So
awesome. Well, I just got to ask, Alberto, does that Mac behind you work?
Yes, it does actually.
Really? Is that
right there?
Yeah.
It's all SE30. I brought it with me wherever I go. He came back from I'm in Baltimore and I came back from California. It actually does work. It has a hard drive. It's a complicated. I cannot boot it now, but next time I'll have it on actually.
Oh, that is so cool. I had a 512K Mac when it first came out.
I did too, but then it died, and this is the only one I could. This is SE30, which was supposed to be has 8 megs of RAM. That's awesome.
Oh wow! Talk about a blast from the past. Okay, but well, that is really cool. Okay, well, it's good to see you again, Alberto. So let me introduce our guest. Well, before I introduce our guest, actually, let me tell you that we want you to interact with us. This is a Hangout on Air, and this is a social media thing that Google and YouTube let us do. So we don't want to just sit here and talk to ourselves. We would like to hear from you guys, and there are several ways that we can interact with, that you can interact with us. One of them is by using the Q&A app, where there's a button as you're watching this that you can click on. It's called it says Q&A on it. If you click on that and then type in your question, it will appear magically before me on my window, and I'll see it, and I'll either read it out if it's a comment, or I'll ask our guests if it's a question. So we can do that throughout the Hangout. Also, I'm monitoring the Future in Space hashtag, as you can see right down there. Future in Space. So that's on Twitter, so you can do that as well. And I'm also looking at the event page on Google+, so leave your comments there as well. Okay, so let me get started here and introduce our guests. First up, I'll have Dr. Jonathan Gardner. He is the chief of the Observational Cosmology Lab at NASA's Goddard Space Flight Center, and he's the Deputy Senior Project Scientist for the James Webb Space Telescope. Welcome. It's good to have you here, Jonathan. Thanks for joining us.
Thank you. I'm very happy to be here.
Also with me is Dr. Matthew Bolkar. He got his PhD in optics from the University of Rochester in 2009, and he's a member of the Wavefront Sensing and Control Group, also at Goddard, and he's currently working, among a great many other things, he's the chief technologist for the Advanced Technology Large Aperture Space Telescope, also known as AT-LAST. Hello, Matthew.
Hi, thanks a lot for having me.
I'm glad you guys could both make it. I'm excited to get started. So, space telescopes. We've got a lot. Anybody who knows anything about building one, and a lot of people on this panel do, we know that they're not very easy to do. The Hubble Space Telescope's been up for 25 years, giving us great views. I'm not sure though, Alberto, was that the first telescope ever? The space telescope?
No. There were many. There were others actually. Actually, it's interesting. It's the story. It's kind of interesting. There were a few astrophysical telescopes built in the 60s and 70s. Of course, not as good by any means as the Hubble Space Telescope, but
so it wasn't the first, but it's definitely the best, right?
It's definitely the best. I would actually argue it's definitely the best by far. Look at it, 25 years, 5 service missions. I mean, it's remarkable, absolutely.
Right.
Change astronomy, right?
That's right. So, and now, of course, we are working on the successor to Hubble, which is we're calling it, which is the James Webb Space Telescope, and it is currently being built both by. Well, but why don't you explain the dynamics, Alberto? Northrop Grumman is a major contractor for it, but it's being assembled in Goddard, right?
Well, it depends. I mean, the different pieces are being brought together. I think I'm going to ask John to give us an update in a second, but I think what's happening is that the telescope, as you mentioned, it's a very large endeavor that takes contractors like Northrop Grumman and others to build the telescope for NASA. But ultimately, there's a collaboration between NASA and industry to actually build this incredible telescope. And so part of the telescope is being built at Northrop Grumman, is being now shipped to Goddard for integration for many things are happening, and so it's a collaboration. I don't want to single out anyone. It's a true collaboration. And then recently, part of what was at Northrop Grumman for some time has been actually shipped to Goddard, and I can actually show you a webcam as I asked John to give us a little update on what's actually going on Webb right now and what we're going to look at.
Okay, go ahead, Jonathan.
Sure, yeah. In fact, it's not just a partnership between NASA and industry, but we also have the European and Canadian space agencies involved. So this is a worldwide project. Many years ago, NASA put out for bid the selection of the prime contractor and selected Northrop to build up the observatory. And in the webcam, the thing that you see down in the lower right is the backplane of the telescope. That was recently shipped from Northrop out to Goddard, and it's in our clean room, where the webcam shows you what's in the clean room. And
so this is live. This is live right now, then, right?
This is live. Yeah, we feed a live image, a still image, every 60 seconds. So this is what's happening right now. And starting in about a month from now, we will start putting the mirrors onto that backplane. Right now, we're building up some harnesses and cables, electrical cables, and so forth. And then, in about a month, as I said, we're going to move that that black structure into the middle of the big yellow.
There you go.
Yeah, the big yellow thing, and we'll start installing the gold mirrors onto that backplane. The other thing that you see just off to the left, it's a little bit smaller, and that's the instrument compartment that we call the ISIM. There are 4 cameras on Webb.
Can you circle that, Alberto?
Yeah, so it's this right here.
Okay.
Okay, yeah. There are 4 cameras. They've all been completely done. 2 of the cameras came from Europe, 1 from Canada, and 1 was built here in the United States. And these are the cameras that will take the pictures and do the spectroscopy, breaking the light up into its individual wavelengths, where we can really use that to get at the physics of the stars and galaxies we're looking at.
Okay, so just to make sure I'm understanding, where Alberto is pointing is the ISIM, the integrated, what does it stand for again?
Integrated Science Instrument Module.
Thank you. And then the backplane, the thing that's basically the skeleton of James Webb, goes right there off to the right there that he's circling.
That's the support for the mirrors. So the light comes from the distant stars and galaxies. It bounces off the large primary mirror, which is made up of 18 hexagonal mirror segments, and the total size of that is 6.6 meters across. So this is by far the largest space telescope that will have ever flown. And then the light bounces off the primary mirror. It goes to a secondary mirror, which will be on a support structure, and then in through the center of the primary mirror into the instruments, which at that point will be installed behind the mirror. And then the instruments record the data. It's sent to the spacecraft and then sent down to Earth, where the scientists can analyze it.
So you were saying that so a lot of this is going to be starting next month. They're going to be putting a lot of the mirror segments on there.
Next month we start putting the mirror segments onto the backplane. So watching the webcam over the next 3-4 months will be very exciting. There's a lot going on in our clean room.
Yeah, this it's starting to ramp up now, isn't it, Alberto?
Yeah, starting to wrap up is actually great because one of the things that maybe I can share it again, but I wanted to show. Let me see if I can show this this image of the backplane a little bit. Hang on a second. Let me share this. But the other interesting, the incredible thing is going to be, at least to me, that the things are really coming together. This is the year we actually build the observatory. This is the webcam, but this is the structure that John was mentioning, fully extended. This is the backplane with the secondary mirror structure. I don't know if you can see that picture.
Mm-hmm. Yep, I can see
Right,
it.
so that holds the secondary, and that is a deployed structure. So it's launched all folded up. So not only do we have the two side wings of the primary mirror, but the secondary spider that you can see in that picture, that's all folded up as well, and we unfold that after it's out in space after launch.
Yeah, Northrop made a really cool animation talking about showing the deployment of JWST, which it's all over the place on the web. But if you can just do a search on JWST deployment on YouTube, you'll be able to see it. It's really a beautiful.
So
setup.
it's a year when things are going to come together, and actually in the webcam image that John was mentioning, I don't know if you can see here, but in the upper right corner there's a window, right? So which is the window at Goddard. So all the visitors will actually be able to see in real time what's happening, and the mirrors being integrated, which is going to be fascinating.
Yeah, we need to do.
I'd love to go over there and look through the window and see it all up close.
Exactly. So
the entire telescope is being assembled there?
The telescope and the instruments are here at Goddard, and we will be putting together the telescope, as I said, over the next 3, 4, 5 months or so. Meanwhile, we are going to put all the instrument compartment, which is completely assembled, we'll put that into a thermal vacuum chamber, bring it down to its operating temperature of 225 degrees below 0 Celsius, and put the instruments through testing through their paces, take images and make sure that they all work properly. That's happening at the same time, and something like next March or April, we will put these two things together, start putting those two things together. It then goes, once it's completely assembled, this is the telescope plus the instruments. When they're completely assembled, we ship it down to the Johnson Space Center in Texas and test the telescope and the cameras both together. Meanwhile, out at Northrop Grumman, they're building the spacecraft and the sun shield. The spacecraft kind of keeps the observatory in its orbit and also handles communications with the Earth, sending the data down. And the sun shield protects the telescope from the sunlight, which allows it to cool down to its very cold operating temperature. So that's the spacecraft and sun shield are still out at Northrop. And we'll put the whole thing together, the whole spacecraft and observatory together, sometime in 2017, early 2018. And then when it's all completely done, we ship it down to South America for launch.
That's right. It's being launched in 2018 from French Guiana on one of the Ariane rockets, I believe. Correct?
Yeah, that's part of the European contribution.
Right. So this thing is starting to come together. I mean, before all these little individual pieces were being built, and now they're starting to be assembled into a larger unit. The backplane that Alberto was showing us, what's that made of?
So it's
me? Go ahead.
Anybody?
No, go ahead, John. Yeah.
Yeah, it's a carbon fiber sort of ceramic structure, very advanced material. Everything we put in space, of course, has to be as lightweight as possible, as low mass, I should say, once it's out in space, because mass is everything. We only have the size of the rocket we have, and we want to put as much stuff onto it as we can. So we want lightweight materials, but in addition to that, it has to be strong and it has to be stiff. So the backplane is a carbon fiber ceramic. The mirrors themselves are made of beryllium, which is a metal. It's atomic element number 4, and it's also very lightweight, very strong, very stiff metal. And then the surface of the mirrors is coated with gold, which is very reflective in the infrared. So all of the materials that go into a space telescope tend to be, the very most advanced materials, lightweight, strong, and then the other thing is we don't want them changing their shape when they go through temperature changes.
Right, because as you mentioned, these things they have to be out there. They're operating in space, and it's cold out there. So you've got to be able to be strong as well as operating at very extreme temperatures.
So
I can
so
see it's both hot and cold out there. It depends on, I suppose, where you are, right?
that's why we have a sun shield, to cool.
Yeah,
Right,
the Webb is going to be hot on the sun side of the sun shield and very cold on the telescope side.
Okay, so did you have something you wanted to add, Alberto?
No, I just want to say that I find every time we describe this, I find it kind of mind-boggling. It's a delicate dance that we all have to play to build this incredible observatory, and every time I think about it, the complexities are tremendous. From structures that cannot change more than a few, than a few nanometers when they go from room temperature to 250 degrees below 0 Celsius or so, to things that have to be coated with gold to increase reflectivity in infrared. I mean, this is ingenuity, human ingenuity at its best. I think it's fantastic.
I know, and it brings out the best, I think, in all of us. So, Jonathan, before we leave this topic, I want to go on to some other space telescope topics here in just a minute. But before I do, you've given us a status report on where things are currently sitting. Is everything on schedule? Is everything looking good? Is there anything anything that stands out as far as red flags or anything like that?
We're doing very well on schedule right now. We have a plan that gets us to launch in October of 2018. That's been the same plan for the last 4 years. And one of the things we do to make sure that we stay on schedule is that we have some margin built into the schedule. We have actually a total of 9 months now that is time set aside to fix any problems that come up. So the next big thing, as I said, is the thermal vacuum test of the instruments. That starts sometime in November, and building up the mirror starting mid-October, about a month from now. Those are both very complicated things, and so we have allocated an extra month or so onto the end of the plan before we have to go on and do the next step. And we've done that all the way through to the launch date in October 2018. And as I said, we've got 9 months to fix any problems that come up.
Right.
So we're actually in very
well.
good shape for the schedule.
Yep,
Oh,
we're doing
good.
very well.
So I will just mention to people now that one of the things, because this is such a big year for JWST and it's the start of a lot of things happening quickly, I'm trying to get, working with Alberto and others, to maybe have some more regular JWST-themed hangouts to keep you guys informed on the progress. So stay tuned for that. I'll let you know how it goes as we get them more fleshed out. But we want to try and keep you guys more informed on how these things are
We'll
done.
just sit you in the front there at Goddard to look at the mirrors being placed on, and
I know
happy there.
you keep promising that, but I have yet to be.
No, we
in
can.
front
Oh,
of
come on! I got a badge now, so we can go in. Come on, let's go in. It's. I want to go. I haven't seen it yet. I've seen it many times at Northrop, but I want to see really the assembly of the mirrors now.
So do I. Actually, I want to do that. So hopefully we'll be bringing more of that JWST related stuff here in future hangouts. But so let's take a step back for a second. So we've talked a little bit about we're building the James Webb Space Telescope. Before that, obviously Hubble Space Telescope. There's been many great observatories put up in space since. There's been Kepler. Well, that's not a great observatory. There's been but Kepler is a space telescope. There's also Spitzer and Chandra. And other telescopes built and put in space for specific purposes. But let's talk a little bit about how this stuff gets started. I mean, who wants to comment? And maybe Matthew, I get you involved in the conversation here on this. When a space who decides, first of all, what space telescopes we need, and then how do they start to build them?
Yeah, well, I mean, it really is the scientific community that decides what's going to happen next. I mean, every 10 years we have this thing called the decadal survey.
Yeah, we've talked about that periodically.
Yeah, so it happens. It's actually on the decade for the astrophysics program. So the last one was in 2010. The next one will be in 2020. This is run by the National Research Council, and they basically solicit input from the community saying, what do you guys think is important to study? What kind of questions do we want to answer? And then, propose type mission architectures or concepts to try to answer those questions. And then the committee sits down and looks over them and kind of decides either, both on scientific merit and technical readiness and programmatic readiness, which one might be the next priority. So, a good example of that is James Webb, which in I believe 2000 was selected as the decadal priority mission and then became the next mission.
So 15 years ago,
15 years, yeah.
The astronomers sat around and decided, hey, wouldn't it be great if we had something like James Webb? And now here we are 28, maybe 18 years later, it'll actually end up being in space.
Yeah, exactly. And in 2010, the priority that came out of that survey was the WFIRST mission, the Wide Field Infrared Survey Telescope.
Oh, yay, you did it.
And that's coming up. Yeah, I don't think it's been, that's sort of anticipated to be something like a mid-2020 launch. So again, about a 15-year delay from selection to launch. And then, obviously now we're in the process right now preparing for the 2020 survey to provide input on what we think the next priority should be.
But it's also true that this worked out for, Hubble was the recommendation for the decadal, and so was Spitzer.
When was Hubble first recommended? Back in the 70s or something, or?
It's like, I actually don't know.
I think it was 1980.
I think it was 80. Yes.
Yeah.
And it was launched in 1990, so that was only 10 years there. So that worked out pretty good.
Might have been 1970.
Yeah. Yeah, it was quite.
I think the average is 15, 17 years or something for missions of this size.
All right, so every 10 years, a bunch of astronomers get together, presumably most of them, they're not just some blessed group, I suppose, get together and they decide, okay, gosh, here's the science questions we want to answer. Here are the things we want to know about the universe. How are we going to go do it? And then Matthew sort of hinted that one of the criteria in deciding what the priority is that, well, can we build it? But James Webb, is my understanding, they said, hey, we want this giant telescope in space, but we're going to have to invent some stuff to make that go, right? I mean, the stuff didn't exist that currently needed to happen for James Webb, right?
Absolutely, yeah. We formally had to invent 10 different things. I'm not sure I can mention them all off the top of my head.
Wait a minute, but that's still amazing. 10 things that
10 inventions, yes. So they were things like large, lightweight mirrors, the detectors, both the near-infrared detectors and the mid-infrared detectors. We had to build those up to larger formats. One of the really cool technologies in Webb is a micro shutter array. This is a 250,000 little moving parts on a computer chip, little windows that we can open up where we want to let the light through to the camera, and where we can close the other ones so that there's not confusion between different spectra. So that was an important invention that we had to create. And then there were other things, the cryo cooler that keeps the mid-infrared instrument cold.
I can think about, sun shield, for example, developing these membranes, for example, large size of a tennis court membranes that need to be stowed and deployed. Even the entire deployment sequence, if you will, it's something that has never been tried before, with this sort of complexities. And then also, John mentioned, the integration of the spacecraft itself, the things that carries, power and pointing and so on and so forth, has to be taken to L2 with very, very strong requirements in terms of stability at the nanometer level, which has never been attempted before. So it's there are things that perhaps we knew, maybe Matthew can comment, but I think we knew we could do, but they needed to advance. We needed to advance the technology to prove that we could do it.
Yeah,
Another
exactly.
thing that's important is that it's not only that we invent something that has to work on Earth, but it has to work out in space, and in the case of Webb, it has to work at
At, at cryo.
225 degrees below zero, very cold
Yeah,
temperatures.
that's a great point.
Yeah,
Okay,
I
but
was
go ahead,
going to just
Matthew.
say real quick, the technologies were invented, but a lot of these, NASA speaks in terms of these things called technology readiness levels, and so generally it's we have a technology that exists at a certain maturity, a certain TRL. One is I had an idea and I wrote it down on the back of a napkin, and 9 is it's flying in space. And so when we say we developed or we invented these technologies, we're talking about maturing the technology through these levels of readiness to the point where they're ready to be actually flown on a mission.
Oh, good. Well, that's an important point because as we're talking about this, I'm thinking there has to be a limit to this, right? I mean, I personally would like to have a transporter, but I can't just suddenly make that a priority. Go, you know what? I'm gonna have, well, I guess we'll have to invent it then. There has to be a level. So you're saying that these technology readiness levels, or they're already given a grade, like it's a measure, I guess, of can this even be done?
Sure.
Mm-hmm.
So they're 1 through 9, and basically the first 3, 1, 2, and 3 are the very sort of, like I said, you had an idea, you kind of shown a proof of concept. It's not completely crazy what you're suggesting, and then 4, 5, and 6 is sort of the real kind of hardware development and showing it out on a real relevant environment, breadboard that relates directly to the mission you're doing. And then 7, 8, and 9 are typically reserved for actual flight missions where the technology is on the spacecraft and then flown and then working on orbit.
Yeah,
Okay,
so the TRL-6 is an important milestone. That's where we put it into a relevant space-like environment, usually in a vacuum chamber, and show that it actually works in a vacuum and at the relevant temperature.
Right.
Now, I just want to bring that up a little bit too, because at Johnson, where this chamber is, it's huge. It's what they used in the Apollo program, right, Alberto? And
Yes.
this is where you could suck all the air out and then cool it down to something really cold, and it's a big cavern that I guess it's one of the only things that James Webb will fit into, and that's where they'll be doing a lot of this testing. But my question is now, okay, so a bunch of astronomers have gotten together. They've said, okay, here's the science questions we want to answer, and they've prioritized them. And then all the technologies required get listed out and given a score that Matt mentioned. And then we decide if it can be built or not. What happens when you go to build something, or does it even happen, and what you invented doesn't work? I mean...
Does
that ever happen?
Come on, that never happens.
Oh, come on. Every invention.
Of course it does.
Every invention always works.
Everything always works the first time. Come on.
Oh, okay. So that's built into the project then. We just
Of course it does. I think that's part of of how engineering progresses. I think I think what really the TRL levels are to me is a kind of a probabilistic determination of how likely you are to be able to build them, and that's why I think what John was saying is TRL-6 is a really important threshold, beyond which you can demonstrate actually something that just doesn't work in an environment like Earth, but can be either demonstrated to work in an environment like space. And remember, for some of this mission that we're talking about, we talk about HTST at L2, so 1 million miles away, 1.5 million kilometers. The conditions are not exactly the ones you have here on Earth. They're a little colder, a little farther, and so there are lots of requirements that need to be established. And so I think, when you cross that threshold, you're in an environment where you think you can demonstrate that technology being viable.
That's right. So for those of you who don't know, L2 is this point where 1.5 million miles away, where we're going to be putting the James Webb Space Telescope. It's not going to be in orbit around the Earth like Hubble is. It's going to be very, very far away, and that's because we need it out there so that we can get it really cold and be not bothered by some of the signal and noise that's around the Earth. And so there's a lot of good science reasons for putting it that far away. In fact, it's a very valuable piece of real estate, it turns out, because it not only is a good place to put a space telescope, it's a safe place to put a space telescope. One of the things everybody worried about, and I asked Scott Willoughby this from Northrop Grumman about a year ago, and he gave a great answer. Jonathan Ehrenberg, also the chief engineer, also answered that L2 is actually a pretty safe place as far as things like flying meteorites or little, space junk, things like that running into it.
Yep.
It's a pretty safe place to go. So that's why we're what's going out into that area of space. So I want to go a little. All right, let's expand a little bit now. We've been talking about JWST almost this entire time, but there's other things being developed right now, and among them is this thing that Matt's working on. It's called ATLAST, Advanced Telescope Large Aperture Space. No, Advanced Technology Large Aperture Space. That is a very awkward acronym, by the way. I don't like
it's probably not going to be the long-term acronym.
I hope not. I hope they turn it into something like Super Space Telescope or something.
Yeah, it actually goes by something now. So yeah, I mean, what you're seeing right there is a concept of one particular.
So that's it. Alberto's got a picture of it up here. This looks like a big trampoline.
It's a concept, yeah. Yeah.
That is one particular concept, and we actually have several architectures that we're looking at. This is what we call the scalable segmented architecture, which leverages.
It looks like James Webb on a trampoline.
Pretty much, yeah. It's James Webb, but a little bit bigger. So you add one more ring of mirrors about it, and that brings you up to about 9.2 meter diameter aperture. It's got a large sun shield. One major difference between this and James Webb is that this is a room temperature telescope. So we're talking about a warm, not cold infrared like James Webb is, but operating in the.
Why is that such a big deal?
Mainly, well, what it comes from is the science goals for this mission. This is a UV visible near-infrared telescope, so very similar to the range that Hubble covers.
Ah, okay, good.
And so because it's in that range, it doesn't need to be cold.
Right.
And since it's not cold, that really simplifies the integration and testing, so we don't have to do all these cryo tests that Jonathan was talking about.
Well, is that a heat shield there underneath it? What is that?
That is mostly a stray light shield. It is a sun shield, so it does.
Sun shield. I got to get away from heat shield.
So the sun stays on one side and the telescope stays on the other side, and it's mostly to keep the sun out of the telescope.
But I guess one thing I want to actually point out here is of course there's a resemblance to JWST, but you can argue that through the process of the decadal survey and the missions that have been built, all the observatories and JWST, we learn. And part of the learning process is that we can reuse. We can figure out how to launch telescopes that are much larger than JWST in space by segmented the mirrors, for example, and fold, secondary mirrors and fold sun shields. And I think so. To some extent, JWST, while it's it's leading in terms of the development of very complex observatory, is just the next step into what is going to feed to this new designs.
Yeah, exactly. Exactly. So, and like you pointed out, this looks a lot like James Webb, and we are definitely using the lessons learned from James Webb to incorporate here things like the deployment system, the segmented mirrors, the sort of instrument package, the wavefront sensing and control that's going to align the system and maintain it on orbit, that sort of thing.
Okay, so you're leveraging a lot of what we learned from JWST. That's cool, but anything got to be invented for this thing, or is it all pretty much off the shelf?
Nope,
it's off the shelf, and so we're done.
No, so as Jonathan mentioned, they had 10 technologies they had to invent. We have a few as well, depending on how you count them. We have 5 major categories of technology. And they're really related to the kind of science that this telescope is planning that we want to accomplish with it. So I think you mentioned earlier you had Mark Postman and Jason Tumlinson on here talking about the HDST, the High Definition Space Telescope.
Right.
ATLAST is a incarnation of HDST. It's one possible architecture that HDST might look like. And so the science goals are the same. We want to do broad, general astrophysics observations, much like Hubble Space Telescope, with the killer app of being able to directly image Earth-like planets around other suns and potentially look for the signs of life on those planets through spectroscopy.
Okay, so I want to highlight that for a second, because this is part of the technology part, where the advanced technology part, to directly image an Earth-sized planet. These things are tiny, and you really do need one of the limiting factors in what you can resolve with the telescope is the size of the aperture of the primary mirror, along with whatever wavelength that you're trying to look at it with. Those are the two big factors in whether you can resolve an object. And also, though, if you're going to directly image a planet, we had this on our hangout yesterday where we were talking about Eridanus 51b. You have to get rid of the bright light of the star, which is and that's you need another piece of technology, which I'm sure you were getting to, and I interrupted you, on called coronagraphs, right? This is where you block out the light from the star so you can see what's around it, correct?
Exactly. So in order to directly image a planet, you need to suppress the starlight, and so a method of starlight suppression is required. And we actually have two in our technology plan that we're looking at that are separate but equal in terms of what they're capable of doing. They each have their advantages and disadvantages, and one of them is an internal coronagraph, and the other one would be a star shade.
So before you talk about each of them,
Yep.
I guess Matthew, why don't we sort of frame the problem first, because we mentioned this before. I think it's worth mentioning again.
Mm-hmm.
I guess if I go outside and put my hand in front of of me blocking the sun, I don't think that's going to be good enough, right, for a telescope. So what kind of suppression are we looking for, and why? What is the relative scale, basically the brightness of the parent star and versus the planets we're trying to image?
Right. So if you were 10 parsecs away and looking back at the solar system, the Earth would be about 10 billion with a B times fainter than the sun. So it's a 1 times 10 to the 10th.
To the 10th, right.
Suppression. That's the order of magnitude difference in brightness between the Earth and the sun.
You're trying to see something billions of times fainter than the star that it's in orbit around.
So we basically have to figure out that to shape my thumb, or to create a thumb that is that it can remove 10 billion times the light for the parent star in order for us to see those few pixels are those planets, and that's very, very hard.
Yes, it is extraordinarily hard, as we're finding out.
But as you said, Matthew, there are two ways to do it, right?
Yep. Yeah. So the first one is what we call an internal coronagraph, and this is actually an instrument that would go inside the telescope. And the coronagraph, the way it works is it takes the focused starlight and basically blocks it, so that you prevent the. I think if you can pull up that slide, that I can show it.
Yep, I have it up.
Yeah, so basically, if on the left there, if you're coming into that little optical system, that's the light from the star. It comes to focus, and we put a little occulting spot right at that focal plane to block the starlight. And there's some optics downstream then that actually help clean up the beam further. But the idea is that you're blocking the starlight while letting the planet light through, and you're doing that well enough that you block 10 billion times the starlight. To the 10 billion photons from the star versus the 1 photon that gets through from the planet.
Right.
So this is one method. It's the strength of this technique is that it's inside the telescope, and so you can, as quickly as you can repoint the telescope, you can observe that many different star systems, that many different planetary systems.
So do you have to stop the light before it gets to the detector, or could you use these micro shutters like what JWST has, maybe just not use the light from that star? Can you do that at all, or?
I mean,
is that just not? Am I not thinking about these micro shutters?
The problem is it's 10 billion times.
Yeah, exactly.
So that's an awful lot
The light doesn't work.
to stop. There are coronagraphs on Hubble, and there are going to be coronagraphs on Webb, and they'll work at sort of the 1 in a million level, or maybe 10 million. But to get 10 billion, that's hard. That's a new development, new technology.
Yeah.
So are you going to talk about what At Last will have, or you want to go on to a?
Well, so the goal for At Last would be to have a coronagraph or a starlight suppression system that is capable of achieving that 10 billion to 1 suppression rate.
And this would be an internal coronagraph then?
So that's one method. The other method I mentioned is the star shade.
Put that up, Alberto.
Before you move, I'm gonna put it up. But before you move on, I also wanted to say that that the coronagraph is also very hard. It has the great advantage, I think, is it's internal, so you can move and go anywhere you want. But but it also has the disadvantage, if you will, that is if the telescope is not that stable, you have to keep the telescope to a stability for you to be able to reconstruct that image, right?
Right.
So there's some sort of what do you call it? Things you have to take into account that are non-trivial in lots of ways.
Right. So earlier, Alberto was talking about the James Webb having to be sort of on the stable on the level of nanometers. If you're going to work with a coronagraph, you need stability on the order of picometers. So 3 orders of magnitude more, or 2 orders of magnitude.
And I mentioned this because that's another technology that we don't have right now, and that we have to develop.
What do we mean? Star shade, or?
For the stability required for the coronagraph.
Oh, I see. Okay. All right.
So the alternative to the coronagraph would be to use the star shade, which Alberto's got that slide up, and the main advantage to the Starshade is that it does not have this stability requirement. Any, Hubble could work with a Starshade. James Webb could work with a Starshade. Any off-the-shelf telescope could work with a Starshade.
Because it's not part of the telescope.
Exactly.
You just hang it out there in space. How big is this thing? This thing looks huge. Is it as big as it looks?
So that particular design that's being shown there is actually from a probe study that was used for the EXO-S, the Exoplanet Starshade mission. So there you're talking about I think it's a 1 to 2 meter telescope, and the Starshade is on the order of 30 to 40 meters, somewhere in that range.
30 to 40 meters. So that's pretty big.
Yes.
So
but that's for only. I mean, and it changes, which is the other drawback of the Starshade, or at least the complexity. It changes as a function of the size of your telescope.
So for at last, if we put at last in the 10 meter aperture range, then the Starshade would have to be in the 80 to 100 meter range.
So it's a function of the kind of. Can you just scooch it further out?
There's some adjustment, but it's not quite that.
Yeah.
Oh, okay.
Yeah.
So
I mean, the requirement is that the spacecraft has to be in the shadow
exactly
of the Starshade, basically.
I know